Hello. In this lecture, we discuss authentication using a key distribution center. So, what is the need for a key distribution center? Suppose two network nodes, say Alice and Bob, want to securely communicate over a network. Then we have seen that they need to first agree on a shared secret key. Let's call it KAB. So, subsequently, they can authenticate using one of the protocols that we discussed. So, how do Alice and Bob agree on a shared secret key KAB? One way is to use public key cryptography, but this requires public key infrastructure. We will discuss public key infrastructure in subsequent lectures, but for now we assume that no public key infrastructure is available. So, in general, public key infrastructure may not always be available. So, we also require authentication protocols in the absence of public key infrastructure. So, suppose there is no public key infrastructure available, we want a mechanism using which any two nodes in a network can agree on a shared secret key. So, one way to do this is to use a trusted node called a key distribution center. So, this is a trusted node at which the secret keys of all the users are stored. That is, key distribution center shares a secret key with every node in the network, say Alice, Bob, and so on. And there may be a key distribution center present in a local area network, which facilitates secure communication between all the nodes in the local area network. So, this key distribution center is an entity that is present inside a network, such as a local area network, which facilitates secure communication among the nodes of that network. So, whenever a new node is installed in the network, the new node and the KDC are configured with a shared secret key. This configuration may be done either manually. For example, the system administrator might type a secret key into the KDC and the same secret key into the node, or via post and so on. So, if the KDC is far away from the newly added node, then the secret key might be sent by post to the new node. So, using one of these ways, that newly added node and the KDC are configured with a shared secret key. This shows the KDC along with different nodes in the network. This is the first node in the network. It shares a secret key alpha with the KDC. This is another node in the network. It shares a secret key beta with the KDC. So, for example, only this node and the KDC know the secret alpha, only this node and the KDC know the secret beta, and so on and so forth. So, every node shares a secret key with the KDC. Now, if node alpha wants to talk to node beta, so notice that we are denoting the nodes by alpha, beta, gamma, and so on, as well as their secret keys by alpha, beta, gamma, and so on. So, if node alpha wants to talk to node beta, then first alpha connects with the KDC, because the KDC knows a secret key with beta as well as one with alpha. So, alpha can securely communicate with the KDC. So, alpha securely communicates with the KDC and asks for a key with which to talk to beta. Notice that alpha cannot directly contact beta because it does not have any shared secret key with beta yet. So, then the KDC authenticates alpha. The KDC can authenticate alpha because alpha and the KDC have a shared secret key. Then the KDC chooses a random number, let us call it R alpha beta, and then sends R alpha beta after encrypting it to alpha. So, the KDC selects a random number R alpha beta, which will serve as a secret key for the communication between alpha and beta. And the KDC encrypts that key R alpha beta and sends it to alpha. The KDC also encrypts and sends the same key R alpha beta to beta with the instruction that it is to be used for communicating with alpha. So, once this is done, then alpha and beta both know the secret key R alpha beta, and they can use it for communication among themselves. Another way is, instead of the KDC having to contact the node beta separately, the KDC can encrypt R alpha beta and pass it on to alpha for forwarding to beta. So, when alpha contacts the KDC for a secret key, the KDC provides R alpha beta to alpha, as well as it encrypts R alpha beta using beta's key and passes it to alpha, and then alpha sends that key to beta. Subsequently, alpha and beta have a shared secret key R alpha beta, and they can securely communicate. At this point, alpha and beta have a shared secret key R alpha beta. Then they mutually authenticate and then start exchanging data. They can mutually authenticate using one of the protocols that we discussed in the previous classes. This procedure is an outline with some details omitted. We later discuss in detail protocols for KDC mediated authentication. First, let's discuss the advantages and disadvantages of KDC. Some advantages are when a new user is being installed into the network, or a user's key is compromised and needs to be changed, then there is a single location that is the KDC that needs to be configured. So an alternative is when a new user is installed into the network, the user's information needs to be installed at every server with which the user might require access. This is difficult. So for example, if a user accesses an email server, a web server, a file server, and so on, so in the absence of a KDC, we might require to manually configure the user's secret key at each of these servers with which the user might communicate. So it is easier to just configure the secret key of a newly added user at a single point, namely the KDC. So that's one advantage of a KDC. There is only a single location KDC that needs to be configured whenever a new user is added into the network. But KDC has some disadvantages. So these disadvantages are common to a scenario where there is a central entity which is responsible for functions in a network. So these disadvantages are as follows. If the KDC is compromised, then all the network resources are vulnerable. So notice that the KDC has a secret shared key with every node in the network. So if the KDC is compromised, suppose its database is hacked, then secret keys with all the nodes in the network are lost. So they are known to the attacker. Another disadvantage is there is a single point of failure. Suppose the KDC fails, for example, it crashes, then no new communication can be initiated. But keys previously distributed can continue to be used. However, if the KDC fails, then if Alice wants to initiate communication with some user with whom she has never communicated, for example, Carol, say, in that case, Alice cannot initiate a communication with another user with whom she has never communicated. So that's another disadvantage of a KDC. Another disadvantage is it can be a performance bottleneck because whenever a node wants to communicate with another node, it has to first contact the KDC. So all network nodes frequently need to communicate with the KDC. So it can be a performance bottleneck. So all these disadvantages arise from the fact that there is a central entity that is responsible for some functions. So these are the disadvantages of a KDC. Here is an alternative that overcomes the second and third of these disadvantages. That is a single point of failure and performance bottleneck. Instead of only one KDC, we have multiple KDCs, all of which share the same database of keys. So there are multiple copies of the same KDC at different locations. All of them share the same database. This solution improves upon these two disadvantages. Now there is no longer a single point of failure. If one of the copies of the KDC fails, then one can always connect to another copy of the KDC. It is also not a performance bottleneck because a user is free to connect to any of the copies of the KDC to get a secret key with another user. So the performance bottleneck disadvantage is elevated. But there is a disadvantage that all copies of the KDC need to be protected. Even if one copy of the KDC is compromised, then the secret keys, all the secret keys in the database are lost. So the secrets at all the copies of the KDC are compromised because the same secrets are stored at all the copies of the KDC. There is another disadvantage is there is additional cost and complexity. We need multiple copies of the KDC. Each one incurs some cost and complexity. So that's a disadvantage. Another disadvantage is there is a need for replication protocols. So the same keys have to be stored at all the copies of the KDC. And whenever a key is changed, the change needs to be implemented at the other copies of the KDC as well. So we require some replication protocols which maintain synchronism between the keys stored at all the KDCs. So it ensures that at any point in time, the same set of secret keys are stored at all the copies of the KDC. These are some disadvantages of a KDC. Now we discuss mediated authentication using a KDC. Consider a network in which every user has a secret shared key with a KDC. Suppose a user Alice wants to communicate with Bob, then the protocol shown in this figure can be used. First, Alice sends a message to the KDC saying that she wants to communicate with Bob. Then the KDC invents a key, let's call it KAB, and then encrypts the key using the secret key that the KDC shares with Alice, that is KLS. So the KDC encrypts this message with the key KLS, use KAB for Bob. So now Alice has got the key KAB, which she can use to securely communicate with Bob. And then the KDC also sets up a connection with Bob and sends the same key KAB to Bob after encrypting it with the secret key KBob, which the KDC shares with Bob. So at the end of these three messages, Alice and Bob both know the secret KAB. But this has a shortcoming that it increases the load on the KDC. Whenever any user contacts the KDC to get a key, then the KDC has to initiate another piece of communication to the user with which the first user wanted to communicate. So this increases the load on the KDC, and as we have seen, the KDC can be a performance bottleneck. So hence, the load on the KDC will increase, and it will start providing service slowly to the new connections that are being initiated to it. So this is one shortcoming. It increases the load on the KDC since it needs to initiate a connection with Bob and share KAB with him. So an alternative to this procedure is in the message from the KDC to Alice, that is this message, a ticket is included which Alice needs to send to Bob, and this ticket contains the key KAB encrypted using the secret key KBob. So instead of the KDC having to separately contact Bob, the KDC just provides a ticket to Alice, and then Alice can subsequently connect with Bob and share the ticket obtained from the KDC with Bob. The ticket will make known to Bob the secret key KAB, and subsequently Bob and Alice can securely communicate. So this figure shows the revised protocol, which uses a ticket instead of the KDC having to initiate communication with Bob. The first message is the same as before. Alice sends a message to KDC saying that she wants to communicate with Bob. Then the KDC sends this message, KLS use KAB for Bob. So this part of the message is the same as in the previous protocol. Along with this message, the KDC sends a ticket to Bob. The ticket to Bob is this message, use KAB for Alice, encrypted using the secret key KBob that the KDC shares with Bob. So the KDC sends this message, KLS use KAB for Bob. This part of the message is meant for Alice, and this part of the message, the ticket to Bob, is meant for Bob. Then subsequently, Alice initiates a communication with Bob. She sends the message, I am Alice, along with this ticket, which Bob can use to obtain the key KAB. Notice that this ticket cannot be decrypted by Alice because it is encrypted using the key KBob, which only Bob and the KDC know. Once this ticket is sent to Bob, Bob can decrypt this ticket and obtain the key KAB. Now, Alice and Bob have the secret shared key KAB, which they can subsequently use to authenticate among themselves and communicate. after the protocol shown in this figure is used, mutual authentication between Alice and Bob needs to be performed. So this can be performed using one of the protocols that we discussed for mutual authentication. So the protocols that we discussed assume that Alice and Bob have a secret shared key KAB. So at the end of this message, Alice and Bob have a secret shared key KAB. They can then use one of the protocols that we discussed for mutual authentication. But this protocol has some vulnerabilities. One example is the following. Consider an intruder 2D who stole Alice's key and also recorded this message too when Alice contacted the KDC to talk to Bob. Later on, Alice changed her key, but 2D can still use the old key and the recorded message too to impersonate herself as Alice to Bob. So this is an example of a vulnerability in this protocol. So the disadvantage of this protocol is that, suppose let's call the old key of Alice as JAlice. Suppose 2D stole the key JAlice and recorded this message too when Alice contacted the KDC using the old key that is JAlice. Later on, Alice changed her key to KAlice, but 2D can still use the old key and the recorded message to impersonate herself as Alice to Bob, because the KDC had sent KAB using the old key JAlice, which 2D has stolen. So 2D can decrypt this part of the communication to obtain the key KAB and then send this message: I am Alice, ticket equals K Bob, use KAB for Alice. So at this point, 2D and Bob have the secret KAB shared among themselves. Then 2D can communicate with Bob pretending to be Alice. So this is one vulnerability that this protocol has. We'll discuss improved protocols which overcome this vulnerability. So in summary, we introduced the concept of a KDC, that is key distribution center, and we introduced some protocols for KDC mediated authentication. But as we have seen, these protocols have some vulnerabilities. So in the next lecture, we'll discuss improved protocols for KDC mediated authentication. Thank you.